I was looking at a pull request the other day where a senior engineer tried to implement a persistent state machine inside a model context protocol server, and they completely misunderstood how the connection lifecycle actually dictates the state boundaries. They assumed that because the transport layer was established, the server could just hold arbitrary conversation context indefinitely without the client explicitly passing it. It really highlighted a fundamental misunderstanding of what MCP is actually designed to do. People hear protocol and they immediately project their traditional REST or WebSocket mental models onto it, but MCP operates on a profoundly different architectural philosophy. It is not just another API wrapper. It is a highly opinionated contract for how artificial intelligence models interface with external systems.
That is a brilliant observation, and honestly, it is the exact trap almost everyone falls into when they first start building with the Model Context Protocol, or MCP. They treat the server as a stateful monolithic application rather than a specialized, ephemeral capability provider. Welcome back to Vinkius Labs, everyone. Tonight we are tearing down the core architecture and transport layers of MCP version 1.0. What you just described, Maya, touches on the absolute bedrock of the protocol. MCP is fundamentally built around a client-server architecture, but the definitions of client and server are very specific here. The host application, which is usually an AI assistant or an integrated development environment like Cursor or Claude Desktop, instantiates an MCP client. This client maintains a one-to-one connection with an MCP server. The server's only job is to expose context, like files or database records, and capabilities, like executing a command or fetching an API, back to the client. The critical constraint, and the one that tripped up your engineer, is that the MCP server itself should be as stateless as possible regarding the AI's conversation. The server does not know what the user just asked the large language model. It only knows that the client just sent a perfectly formatted JSON RPC request asking for a specific resource or tool execution. If you try to build conversational memory into the MCP server, you are fighting the architecture. The context lives in the host application. The server provides the raw material.
Exactly. And to really grasp how that interaction flows, we have to break down the entire lifecycle of an MCP connection. It is not just a matter of opening a socket and blasting JSON back and forth. The protocol dictates a very strict initialization sequence that must succeed before any actual work can happen. When an MCP client decides to spin up a connection to a server, the very first thing that happens after the transport is established is the initialization phase. The client sends an initialize request. This is not just a polite hello. This request contains vital metadata about the client, its version, and most importantly, the capabilities it supports. For example, the client might say, I support receiving resource templates, or I support the prompt execution capability. The server then receives this, processes it, and responds with its own initialize response. This response is equally critical because it defines the server's identity, its protocol version, and the capabilities it provides. If the server says, I provide tools and resources, but I do not support prompts, the client now knows exactly what it can and cannot ask for. This capability negotiation is the cornerstone of MCP's extensibility. It allows older clients to talk to newer servers and vice versa without catastrophic failures, gracefully degrading functionality based on the intersection of their supported capabilities. And crucially, until the client receives that successful initialize response and then sends a follow-up initialize notification to confirm receipt, all other requests must be rejected by the server.
That strict handshake is non-negotiable, and it is built on top of JSON RPC 2.0, which is the foundational message format for all MCP communications. For those preparing for the certification, you must understand the distinction between the three primary message types in JSON RPC and how MCP utilizes them. First, you have requests. A request always has a method string, some optional parameters, and crucially, a unique message identifier. When a client sends a request, it expects a response, which will carry that exact same identifier. The response will contain either a result object on success or an error object on failure. The synchronous nature of requests is what you use for asking the server to read a file or execute a tool. But then you have notifications. A notification looks exactly like a request, but it lacks that message identifier. This is a fire and forget message. In MCP, notifications are used for state changes where the sender does not need a confirmation. For instance, when the server realizes that a file it is exposing has been modified on disk, it can send a resource updated notification to the client. The server does not care if the client processes it successfully. It is just broadcasting the state change. And finally, you have the ping message, which is a standard request used purely as a heartbeat to verify the connection is still alive. Understanding these primitives is essential because every single MCP feature, whether it is resource pagination, tool execution, or prompt retrieval, is just a specific schema built on top of these JSON RPC message types.
The JSON RPC layer gives us the vocabulary, but the transport layer is how we actually send the words, and this is where the architecture gets really fascinating. MCP currently specifies 2 standard transport mechanisms, and choosing the right one is the most critical architectural decision you will make when deploying a server. Let us start with the standard input and standard output transport, commonly referred to as STIO. This is the simplest and, right now, the most prevalent transport. In the STIO model, the MCP client actually spawns the MCP server as a child process. It physically executes the binary or the script. The communication happens entirely over the standard input and standard output streams of that child process. The client writes JSON RPC messages to the server's STIN, and the server writes its responses back to its STOUT. Standard error is strictly reserved for human-readable logging and debugging, which the client can capture and display. The beauty of the STIO transport is its absolute simplicity and its inherent security. There are no network ports to open, no authentication tokens to manage, and no firewalls to configure. The server inherits the exact file system permissions and execution context of the user running the host application. If I run Claude Desktop on my local machine, the local MCP servers it spins up can only access what my user account can access. It is an incredibly tight, secure boundary for local development and local tool integration.
The local execution model of STIO is fantastic for personal productivity, but it presents a massive limitation when we move to enterprise environments or remote execution. If you have a massive corporate database, you are not going to let every developer's local AI assistant spin up a direct local connection to it. You need a centralized, governable, and scalable way to host MCP capabilities. This brings us to the second transport mechanism, HTTP with server-sent events, or SSE. This is where the architecture shifts from local child processes to decoupled, remote microservices. Implementing the HTTP SSE transport is significantly more complex than STIO because we are dealing with a unidirectional technology attempting to handle bidirectional communication. SSE was designed for servers to push real-time updates to web clients, not for back-and-forth dialogue. So, MCP solves this by splitting the communication into 2 distinct channels. When an MCP client wants to connect to a remote server, it first makes a standard HTTP GET request to the server's SSE endpoint. The server responds by establishing a persistent server-sent events connection. This persistent pipe is used exclusively for the server to send messages down to the client. That handles the server-to-client half of the equation. But how does the client send requests to the server?
Right, because the client cannot write data back up an SSE stream. To solve this, during the initial connection setup over that SSE channel, the server pushes down an endpoint URL to the client. This is the client's dedicated post endpoint. Whenever the MCP client needs to send a request or a notification to the server, it makes a standard HTTP post request to that specific URL with the JSON RPC payload in the body. The server receives the post, processes the request, and then sends the response back down the persistent SSE channel, matching the message identifiers just like we discussed earlier. It is an elegant workaround for the limitations of HTTP, but it introduces a whole new set of architectural challenges. Suddenly, you have to manage connection drops, network latency, and most importantly, authentication. Unlike the STIO transport, an HTTP endpoint is exposed to the network. You must implement robust authorization layers, usually via standard HTTP headers with bearer tokens, to ensure that only authorized MCP clients can connect to your server. Furthermore, because HTTP is stateless, the server must now manage session state. It has to keep track of which SSE connection belongs to which client, and it has to route the incoming post requests to the correct session context. This is where load balancing and horizontal scaling become non-trivial. If you have multiple instances of your MCP server behind a load balancer, you must ensure that the post requests from a client are routed to the exact same server instance that holds its SSE connection, usually requiring sticky sessions or a centralized pub/sub backplane like Redis to route messages across instances.
That is the exact architectural chasm that separates a toy MCP project from a production-grade enterprise deployment. When you are studying for the certification, you have to be able to evaluate a scenario and recommend the correct transport. If the requirement is local file system access, zero configuration setup, and the capability is strictly tied to a single user's machine, you choose STIO. If the requirement is centralized access control, integration with remote software as a service APIs, pooling database connections, or enforcing corporate governance on what the AI can see, you absolutely must architect around the HTTP SSE transport. And once you move to HTTP, you are adopting all the operational overhead of a modern distributed system. You need observability. You cannot just tail the standard error stream anymore. You need structured logging, distributed tracing to track a request from the large language model host all the way down through the MCP server to the backend database, and rigorous metrics on latency and error rates. Because remember, every time the AI model decides to use a tool, it is waiting on your MCP server to respond. If your HTTP transport layer introduces a 2-second latency overhead because of poorly optimized routing or synchronous blocking operations, you degrade the entire user experience of the AI assistant. The LLM will sit there, spinning, waiting for the tool result to come back so it can continue generating tokens. Performance in the transport layer is not a nice-to-have, it is a hard requirement.
Building on that performance aspect, let us talk about the connection lifecycle during actual steady-state operation. Once the transport is established and the initialize handshake is complete, the client and server enter the standard operating phase. This is where the actual value is exchanged. But networks are inherently unreliable and child processes can crash. The protocol defines a standard ping mechanism to handle this. The client or the server can send a ping request at any time. The receiving party must immediately respond with an empty result. If a certain amount of time passes without a successful ping, the connection is considered dead. For the STIO transport, a dead connection usually means the child process has terminated unexpectedly. The client's responsibility here is typically to alert the user or attempt a clean restart of the process. For the HTTP SSE transport, connection drops are far more common due to network blips or load balancer timeouts. When an SSE connection drops, the client must initiate a completely new connection lifecycle. It cannot just resume the old one. It must hit the SSE endpoint again, establish a new stream, receive a new post endpoint, and crucially, perform the initialize handshake all over again. This means your MCP server must be designed to handle sudden disconnects gracefully, cleaning up any temporary resources or locks it might have been holding for that client, without waiting for an explicit termination signal that may never arrive.
That graceful degradation and cleanup is vital. But what happens when things go wrong during the actual exchange of messages? The protocol utilizes JSON RPC error objects, which are highly structured. An error object must contain an integer error code, a string message, and an optional data payload for additional context. The protocol reserves specific error codes for standard transport and protocol-level failures, like parse errors, invalid requests, or method not found. For example, if a client tries to call a tool that the server did not advertise during the initialization phase, the server should immediately return a method not found error code. However, when you are building custom capabilities, you are expected to use error codes outside the reserved range to signal application-specific failures. If a client asks for a database record that does not exist, you should not crash the server or return a generic internal error. You should return a structured error indicating that the specific resource was not found. This is crucial because the AI model is often the ultimate consumer of these errors. If you return a clean, descriptive error message, the LLM can read that error, understand what went wrong, and potentially adjust its parameters and try the request again autonomously. If you just return a generic 500 status code or a stack trace, the LLM will hallucinate a reason or simply give up, resulting in a poor user experience. The error handling layer is actually part of the user interface for the AI.
That is a brilliant way to frame it. The error message is the UI for the agent. This brings us back to the capability negotiation we discussed at the start, because capabilities dictate the boundaries of what errors are even possible. Let us dive a bit deeper into how capabilities are structured. During the initialize request, the client sends a capabilities object. This object has keys for different feature areas, like routes, sampling, or experimental features. The server's response also contains a capabilities object with keys for logging, prompts, resources, and tools. But it is not just a binary yes or no. The capabilities object can contain nested configuration. For instance, if a server supports resources, its capability object might look like resources, and inside that, subscribe is set to true. This tells the client not only that the server provides resources, but that it also supports the publish-subscribe pattern for resource updates. If the server does not explicitly declare subscribe as true, the client must not attempt to send a subscribe request for a resource. This granular negotiation allows the protocol to evolve over time. If a new version of MCP introduces a completely new feature area, let us say asynchronous long-running tasks, an older server simply will not include that capability in its initialization response. The newer client sees the absence of that capability and safely disables its internal logic for long-running tasks for that specific server connection. It is a masterclass in backwards compatibility.
And that compatibility is what makes the ecosystem scalable. You can have a bleeding-edge host application talking to a legacy MCP server written a year ago, and the protocol guarantees they will find a common ground. Now, regarding termination, we talked about unexpected disconnects, but what about a clean shutdown? While JSON RPC does not strictly define a teardown sequence, the MCP community relies on standard signals for the style transport. The host application will typically send a SIGDERM signal to the child process. The MCP server must catch this signal, flush any pending logs to standard error, close any open database connections, and exit cleanly. For the HTTP SSE transport, termination is usually initiated by the client simply dropping the SSE connection. The server's network stack will detect the closed socket, and the server application should then execute its cleanup routines for that specific session. There is no explicit goodbye message required by the core protocol, which reinforces the design philosophy that the server should be treating each interaction as independently as possible, minimizing long-lived state tied to a specific client connection. The architecture forces you into good habits. It forces you to build stateless, idempotent, and resilient capability providers rather than monolithic state machines.
This has been an incredibly dense breakdown, and it is exactly what engineers need to internalize to master this protocol. We have covered the strict client-server boundaries, the absolute necessity of the initialization handshake and capability negotiation, and the fundamental differences in architecture, security, and operation between the local style transport and the remote HTTP SSE transport. We also explored the underlying JSON RPC message structures and the critical role of structured error handling when interfacing with large language models. These are the core tenets of the Model Context Protocol. If you understand these connection life cycles and transport mechanisms, you can architect integrations that are not only secure and scalable, but also provide the robust, predictable capabilities that advanced AI agents require to function reliably in production environments.
Absolutely correct. The protocol is elegant, but it requires discipline to implement correctly. For everyone studying for the certification or building their first production integrations, I strongly recommend setting up both a style and an HTTP SSE server from scratch, without relying on the higher-level software development kits initially. Handcrafting the JSON RPC payloads and managing the SSE streams manually is the absolute best way to cement this knowledge into your mind. You have to feel the pain of a malformed message identifier to truly respect the protocol constraints. We will be diving into the specifics of resources and resource templates in the next module, which builds directly on the capability negotiation we covered today. Thank you for studying with Vinkius Labs, and we will see you in the next deep focus session. Keep building.
Moving directly into the next phase of our architectural breakdown, we need to transition our focus toward the microscopic level of the protocol, specifically the message types and the underlying data flow mechanics. Now that we have established the transport layers and the connection lifecycle, the natural progression is to dissect exactly what is traversing those pipes. The Model Context Protocol ecosystem relies entirely on a standardized, predictable format for data transmission, and at the heart of this is the JSON Remote Procedure Call version 2.0 specification. For engineers accustomed to building RESTful application programming interfaces or working with GraphQL, the shift to a pure remote procedure call paradigm requires a specific mental model. The protocol dictates that every interaction, whether it is a client querying available tools or a server returning a prompt template, is encapsulated within a strictly defined JSON payload. We need to comprehensively analyze these core message structures, starting with the fundamental trinity of the protocol, which comprises requests, responses, and unidirectional notifications. Alex, could you lay the groundwork by explaining why the architects of the protocol chose the JSON RPC 2.0 standard over other serialization formats like protocol buffers or a custom binary framing protocol, and how this choice influences the payload schemas we construct?
The decision to adopt the JSON Remote Procedure Call 2.0 standard is fundamentally about maximizing interoperability and developer ergonomics while maintaining a sufficiently rigorous structural contract. When you are designing a protocol that needs to be universally understood by varying language models, agent frameworks, and enterprise backends, you cannot afford the friction of requiring specialized binary compilation steps or complex interface definition language parsers just to establish basic communication. JSON is the lingua franca of the modern web, and, perhaps more importantly, it is the native language of large language models. These models are already exceptionally proficient at generating and parsing JSON structures. By using standard JSON, the Model Context Protocol ensures that the barrier to entry for building a server or a client is incredibly low. You do not need massive external dependencies. The standard library of almost any programming language is equipped to handle the serialization and deserialization. However, pure JSON is too unstructured for reliable system-to-system communication. That is where the Remote Procedure Call 2.0 specification provides the necessary scaffolding. It enforces a strict schema that separates the transport mechanism from the application logic. Every message must be an object containing a specific version identifier string. Every request must define a method string and an identifier. This provides a predictable, standardized envelope. If the architects had chosen protocol buffers, while it would undoubtedly be more efficient over the wire in terms of byte size, it would introduce an ahead-of-time compilation step that breaks the dynamic, highly iterative nature of artificial intelligence agent development. The slight overhead of parsing text-based JSON is a highly deliberate, pragmatic trade-off for unparalleled flexibility and ease of integration across entirely disjointed technology stacks.
That pragmatic trade-off makes perfect sense, especially when you consider that the primary consumers of these APIs are often autonomous agents constructing payloads dynamically based on their evolving context. Let us drill down into the absolute anatomy of these messages, starting with the request object. In a standard RESTful architecture, the intent is often split between the HTTP method, the URL path, and the request body. In our remote procedure call model, all of that semantic meaning is collapsed into a single JSON object. A valid request must contain the John property set exactly to the string value of 2.0, an ID property, a method property, and an optional params property. The ID is arguably the linchpin of the entire asynchronous architecture. It can be a string, a number, or even null, although using null is heavily discouraged in modern implementations because it creates ambiguity with parsing errors. The method is a string indicating the name of the remote procedure being invoked, and params is a structured value that holds the parameter values to be used during the invocation. Can you walk us through the operational mechanics of the ID field, specifically how clients must generate and track these identifiers to handle concurrent requests without introducing race conditions or state corruption?
The identifier field is absolutely critical, and mishandling it is one of the most common pitfalls I see when teams build custom clients. Because the Model Context Protocol operates asynchronously, A client might dispatch 5 requests back-to-back without waiting for the first one to resolve. The transport layer, whether it is standard input-output or server-sent events, makes no guarantee that responses will return in the order they were requested. If a client asks a server to execute a simple database query and then asks it to perform a computationally heavy image generation task, the database response will likely return long before the image generation completes. The ID is the only mechanism the client has to correlate an incoming response with its originating request. Therefore, the client must generate globally unique identifiers for every active session. Typically, a monotonically increasing integer or a universally unique identifier string is used. When the client sends the request, it stores the ID alongside a callback function or a resolvable promise in a local concurrency map. When a payload arrives from the server containing a result or an error, the client extracts the ID, looks up the corresponding promise in its map, resolves or rejects it, and then safely destroys that state. If a server returns an ID that the client does not recognize, the client must aggressively log the anomaly and drop the message, because it implies either a severe bug in the server's routing logic or a potential payload injection attack. The strictness around this identifier lifecycle is what allows the protocol to scale to hundreds of concurrent operations over a single multiplex connection.
Building on that concurrency map concept, let us flip the perspective to the server side and examine the response object. According to the specification, when a request is processed, the server must reply with a response object. This object must contain the jump version string, the exact ID that was passed in the request, and then either a result property or an error property. It is absolutely crucial to emphasize that result and error are mutually exclusive. A single response cannot contain both. If the method invocation was successful, the result object contains the payload, which could be an array of tools, the content of a file, or the output of a script execution. If the invocation failed, the error object takes precedence. This mutually exclusive design forces engineers to handle application state cleanly. You do not have to parse a result object to figure out if it secretly contains an error flag, which is an anti-pattern we see too often in poorly designed web application programming interfaces. Alex, could you dissect the anatomy of the error reporting structure? The JSON remote procedure call specification defines a standard error object containing a code, a message, and optional data. How does the Model Context Protocol utilize these standard fields, and how should engineers structure the data property to provide maximum context to the artificial intelligence agent that might be attempting to recover from the failure?
The standardized error reporting structure is perhaps one of the most powerful features of this architecture, particularly because the ultimate consumer of the error is often not a human developer, but a large language model. Let us break down the standard error object. It requires an integer code and a string message. The specification reserves error codes from -32,768 to -32,000 to indicate parsing errors, invalid requests, method not found, and invalid parameters. For instance, if a client sends a payload that is not valid JSON, the transport layer will emit a parse error with the code -32,700. If the payload is valid JSON but does not contain a method string, it emits an invalid request error. Where it gets fascinating for the Model Context Protocol is the application-defined errors, which use codes outside that reserved range. When a server encounters a domain-specific failure, perhaps a tool execution failed because a file was locked or an external application programming interface rate limit was exceeded, the server should return a custom error code and a highly descriptive message. The optional data field is where you inject your operational telemetry. Instead of just saying that a database query failed, the data field should contain the exact structured schema validation error, the missing required parameters, or the retry after headers. Why is this so vital? Because when an agent receives an error response, that exact JSON payload is injected back into its context window. If the error data clearly specifies that the parameter file path is strictly required but was omitted, the agent has enough semantic understanding to autonomously rewrite its request, include the file path, and try again. Your error messages are quite literally part of your prompt engineering strategy.
That is a brilliant way to frame it. The error payload is not just a logging artifact, it is an active control signal for the autonomous agent's reasoning loop. Now, we have covered the two-way street of requests and responses, but there is a third, equally important message type in the protocol, which is the notification. A notification is structurally identical to a request, containing the genre string, a method, and params, but it explicitly lacks an ID field. Because there is no identifier, the receiver cannot correlate it with a promise, and therefore the sender must not expect a response. It is a pure fire and forget mechanism. In the context of the Model Context Protocol, notifications are incredibly valuable for transmitting state changes or asynchronous telemetry without blocking the main event loop or polluting the connection with empty acknowledgement responses. I know that resource updates and progress tracking often rely on this mechanism. Could you elaborate on the precise scenarios where a server or a client should employ a unidirectional notification, and what the architectural risks are if an engineer improperly uses a notification when they actually needed a verifiable request?
Unidirectional notifications are designed for high-throughput, low-criticality telemetry where the cost of waiting for an acknowledgement outweighs the value of the delivery guarantee. The most common use case in the ecosystem is progress reporting. Imagine a server exposing a tool that trains a localized machine learning model or processes a massive video file. That operation might take 10 minutes. The client sends a standard request to execute the tool, but instead of the server remaining completely silent for 10 minutes, it can fire off a continuous stream of notifications. These notifications, perhaps using a custom method indicating progress, contain parameters detailing the percentage complete in the current processing stage. The client can use these notifications to update a user interface or inform the language model that work is actively progressing, preventing a timeout cascade. Another primary use case is resource state changes. If a server is monitoring a local file system and a file changes, it can broadcast a notification to any client that has subscribed to that resource, allowing the client to invalidate its local cache. However, the architectural risk here is significant. Because notifications are fire and forget, they operate with at most once delivery semantics. If the network drops a packet, or if the transport layer buffers overflow, the notification is lost forever, and the sender will never know. Therefore, you must never use notifications for state-mutating operations where consistency is required. If a client needs to cancel an ongoing tool execution, it must send a formal request, not a notification, because it absolutely needs the server to acknowledge that the cancellation was successfully processed and that computational resources have been freed. Confusing those two paradigms will lead to agonizing race conditions and ghost processes lingering in your architecture.
That distinction between state-mutating requests and fire-and-forget telemetry is a crucial boundary to maintain. Let us shift our focus from the abstract JSON structures to the physical data flow mechanics across our two primary transport layers. Understanding how these JSON strings actually travel over the wire is where theory hits reality. Let us start with the standard input and standard output transport, commonly referred to as standard I/O. When we are communicating over standard I/O, we are operating at the level of operating system pipes. The protocol enforces a strictly new-line delimited JSON format for this transport. This means that every complete JSON remote procedure call message, whether it is a request, response, or notification, must be serialized into a single continuous string without any internal new-line characters, and it must be terminated by a single line feed character. This sounds simple, but it fundamentally changes how you handle serialization. You cannot pretty print your JSON payloads because the parser on the other end is simply reading a stream of bytes until it hits a new line, and then attempting to parse everything accumulated in the buffer as a single JSON object. What are the common pitfalls engineers face when implementing stream parsers for new-line delimited JSON, and how do we handle issues like stream back pressure or blocking operations when a massive payload is pushed through standard output? The deadlock scenario is exactly why understanding the underlying operating system mechanics is necessary for building resilient agents. Now, let us contrast that highly coupled, stream-based data flow with the remote transport layer using Hypertext Transfer Protocol and server-sent events. In this paradigm, the data flow is fundamentally asymmetric. The server pushes asynchronous data down to the client over a persistent, unidirectional server-sent events connection. Every JSON message from the server is wrapped inside the data payload of an event stream format. Conversely, When the client needs to send a request or a notification to the server, it cannot use that event stream. It must open a completely separate connection and execute an HTTP POST request to a specific endpoint, placing the JSON message in the request body. This decouples the ingress and egress paths completely. The server receives the post, acknowledges it immediately with a standard HTTP 202 accepted status, and then routes the actual JSON remote procedure call response asynchronously down the established server-sent events pipeline. This complex dance introduces entirely new failure domains. Alex, when we architect the data flow over this HTTP transport, how do we handle network latency, payload schemas, and the reality that a client's post request might succeed, but the subsequent asynchronous response over the SSE channel might be delayed or dropped due to intermediate proxies or load balancers?
The asymmetric nature of the HTTP transport introduces a distributed systems problem that the standard input-output transport largely avoids. Because the client's egress and ingress paths are physically separate network connections, the synchronization relies entirely on the JSON remote procedure call identifier. When a client sends an HTTP post, the server's immediate HTTP 202 response simply means the payload was successfully written to the server's internal processing queue. It does not mean the method invocation succeeded. The client must then passively listen on the server-sent events channel for the actual result. The most significant challenge here involves network intermediaries. Corporate firewalls, reverse proxies, and cloud load balancers are notorious for silently terminating long-lived connections if there is no active traffic. If the SSE stream is dropped, the server might process a request and attempt to push the response, but the socket is dead. To combat this, the protocol mechanics dictate strict timeout and retry strategies. The client must maintain a timeout timer for every request identifier. If a response does not arrive within the expected window, the client must assume the transaction failed or the connection is compromised. Additionally, to keep the SSE channel alive through aggressive proxies, the server must implement a heartbeat mechanism, periodically transmitting empty event comments or specialized ping notifications to ensure the network path remains active. Regarding payload schemas, the rules remain identical. The application layer must not care whether the payload arrived via a local pipe or an HTTP post. The controller logic should simply receive a validated JSON object. The transport layer's responsibility is purely extraction and serialization, ensuring that by the time the application layer evaluates the method and the parameters, the data is structurally sound and strictly adheres to the negotiated capabilities schema.
That separation of concerns between the transport extraction layer and the application logic layer is the hallmark of a mature architecture. Let us talk specifically about the schemas enforced within the params and result objects. The Model Context Protocol specification relies heavily on JSON schema, particularly Draft 7 or newer, to define the exact shape of expected inputs. During the initialization phase, when a server registers its available tools, it does not just provide a name and a text description, it provides a rigorous JSON schema defining the input parameters. When an AI agent decides to execute a tool, it uses this schema to construct the JSON payload. If the server is written in TypeScript, for example, it will likely use a validation library to verify the incoming JSON string against this schema before executing the underlying function. What happens at the protocol level when the data flow mechanics encounter a schema validation failure? Does the connection drop, or is there a standardized recovery mechanism built into the message flow?
The protocol explicitly handles schema validation failures through the standard error reporting mechanisms we discussed earlier, rather than through connection termination. Dropping a connection because of a bad parameter is a catastrophic overreaction that breaks the autonomy of the system. If an AI agent hallucinates a parameter name or provides a string where an integer is expected, the server's validation layer will catch this before the actual business logic is invoked. The server then constructs a JSON remote procedure call error response. Crucially, the error code should reflect an invalid parameter state, typically -32602. The error message should be clear, such as indicating the schema validation failed, but the true value lies in the data object. A robust server implementation will serialize the exact validation errors generated by its schema library, detailing the specific JSON path that failed, the expected type, and the received type. This structured error payload is routed back through the transport layer, traversing the standard output pipe or the server sent events channel, and is delivered to the client. The client, which is typically managing the context window of a large language model, injects this entire error structure back into the conversation history as a tool execution result. The language model then analyzes its own mistake, recognizes the schema violation based on the error data, and automatically generates a corrected request. This iterative, self-correcting data flow is entirely dependent on the strict, predictable formatting of both the requests and the corresponding error payloads. Without a rigid schema validation pipeline, the agent would just receive generic internal server errors and fail silently.
This brings us to a fascinating realization about this architecture. It is not just a data transfer mechanism. It is a specialized feedback loop engineered specifically for deterministic communication with non-deterministic systems. The language models themselves are highly probabilistic, but the protocol wrapping them is rigorously deterministic. By enforcing rigid constraints on the JSON remote procedure call structures, the strict schema validation on the parameters, and the standardized routing of error codes, the protocol artificially imposes reliability onto the AI agents. Every request, response, and notification acts as a structural guardrail. Before we conclude this specific section on message types, we must address the absolute limits of these data flows. When we are dealing with system operations, we are not just passing small text strings. We might be asking a server to read a log file that is 200 megabytes in size, or querying a vector database that wants to return 10,000 floating point embeddings. JSON is inherently inefficient for massive binary payloads or gargantuan datasets. How does the protocol design handle these extremes, and what strategies must engineers implement to prevent out-of-memory crashes when the data flow simply becomes too large for a single message payload?
That is the ultimate stress test of any RPC framework. The specification itself does not artificially cap the byte size of a payload, but physics and computer memory certainly do. As we discussed with stream buffering, attempting to parse a 200 megabyte JSON string in memory will immediately crash most Node.js or Python processes. Therefore, protocol implementations must enforce practical limits. A common standard is rejecting any incoming message payload that exceeds a few megabytes. So, how do we handle massive data transfers? We use architectural patterns like pagination and reference passing. If a client requests a massive log file, the server should not attempt to read the entire file into a JSON string and send it as a single result. Instead, the server should implement a pagination cursor in its capability schema. The client requests the first 1,000 lines, and the server returns that chunk along with a cursor string. The client then issues a subsequent request with that cursor to get the next chunk. Alternatively, for large binary assets like images or video, the server should not base64 encode a gigabyte file into a JSON response. The server should write that file to a temporary location on disk or upload it to a cloud storage bucket, and then return a small JSON response containing a uniform resource identifier pointing to the asset. The client can then retrieve the binary data out of band using standard HTTP or local file system APIs. This architecture is designed for control plane operations and semantic context transfer, not for bulk data plane transfers. If you find yourself trying to push gigabytes of raw data through a single JSON property, you have fundamentally misunderstood the architecture. You must use the protocol to orchestrate the movement of data rather than using it as the vehicle for the massive data itself.
That is an exceptional point of clarity to end on. The protocol is the orchestrator, the control plane that synchronizes the intelligence of the model with the utility of the backend systems. By mastering these exact JSON remote procedure call structures, understanding the asynchronous dance of request identifiers, and implementing robust error feedback loops, you are building the unbreakable nervous system that allows AI agents to interact with the real world safely and predictably. It is about understanding the data flow mechanics at a microscopic level so that the macroscopic application remains infinitely resilient. We have thoroughly mapped out the message types and their traversal mechanisms across both local and remote transports. We are now perfectly positioned to examine how these raw messages are actually organized into semantic capabilities.
Exactly. The transition from raw message routing to semantic capability negotiation is where the model context protocol truly becomes intelligent. Up until the connection handshake, the client and server are just two endpoints shouting JavaScript object notation over a transport layer. They have no idea what the other endpoint is capable of, what features are supported, or what the strict functional boundaries of the session will be. This brings us to the most critical phase of the connection lifecycle, which is the initialization handshake. This is not merely a formality. It is a rigorous, cryptographically significant negotiation of state and ability. The very first message that a client must send after establishing the transport layer is the initialize request. If a client attempts to send any other request, such as a tool call or a resource read, before this initialization is complete, the server is architecturally mandated to reject it immediately. The initialize request is a standard JSON remote procedure call message, but its parameters payload is heavily structured. It contains the protocol version the client supports, a client information object detailing the client's name and version, and, most importantly, the client capabilities object.
That initial payload is fascinating because it establishes a bidirectional trust model right out of the gate. The client is not just passively connecting, it is declaring its own identity and its own feature set. When we talk about the client capabilities object, we are looking at specific properties like routes and sampling. For instance, the routes capability allows the client to tell the server, I have a local workspace, and I am willing to expose specific directory paths to you if you need to understand the boundaries of my local file system. The sampling capability is even more advanced. It tells the server that the client is willing to route prompts back to the underlying large language model on the server's behalf. But before we get too deep into the specific capabilities, I want to unpack the protocol versioning strategy. When the client sends its supported protocol version, say version 1.0, how exactly should the server handle a scenario where it is running an older or newer version? Version mismatches are the bane of distributed systems, so how does the protocol enforce compatibility without breaking the ecosystem?
The versioning strategy in the Model Context Protocol is deliberately strict to prevent silent failures and unpredictable behavior. When the server receives that initialize request, it must examine the client's protocol version string. The protocol uses semantic versioning. The server must respond with the version of the protocol that it will actually use for the duration of the session. If the server only supports version 0.9 and the client requested version 1.0, the server responds with version 0.9. It is then entirely up to the client to decide if it can gracefully downgrade its internal logic to communicate using the 0.9 specification. If the client determines that the version disparity is too great and it cannot safely operate, the client must terminate the transport connection immediately. There is no mid-session version negotiation. You agree on the dialect during the handshake, or you drop the connection. This prevents situations where a client expects a specific error code format introduced in version 1.0, but the older server returns a generic string, causing the client's parsing logic to crash entirely. Once the version is agreed upon, the server constructs its own response payload, which includes the server information object and the server capabilities object. This server capabilities object is the absolute source of truth for what the server is permitted to do.
And this server capabilities object is incredibly granular. It is not just a Boolean flag saying, I support tools. It is a nested structure. For example, within the server capabilities, there is a prompts object. If that object is present, it means the server can provide prompt templates. But inside that prompts object, there is a Boolean property called listChanged. If listChanged is set to true, the server is making a highly specific promise to the client. It is saying, not only do I have prompts, but I will actively send you a notification whenever my list of available prompts is updated. This is a massive architectural shift because it moves the client away from a naive polling mechanism. If the server does not declare listChanged as true, the client knows it has to periodically ask the server for the prompt list if it wants to keep its user interface up to date. This dynamic feature toggling directly impacts how we write the client-side state management code. If you are building a robust client, you have to write code that adapts its behavior based on these tiny Boolean flags negotiated during the first 10 milliseconds of the connection.
That is precisely the level of detail engineers need to focus on. Let us look at the resources capability. A server might declare the resources object, meaning it can serve static or dynamic data to the model. Within that resources object, there is a property called subscribe. If the server sets subscribe to true, It means the server has implemented an internal pub/sub mechanism. The client can send a resources/subscribe request for a specific uniform resource identifier, and the server will push notifications whenever that resource changes. Now, consider the graceful degradation aspect of this. A senior engineer building a model context protocol client will write a resource synchronization manager. When the connection initializes, this manager checks the server capabilities. If resources.subscribe is true, the manager hooks into the notification event listener. If resources.subscribe is false or missing, the manager gracefully degrades by spinning up a background timer that sends a resources/read request every 60 seconds. The end user never sees an error. The application remains fully functional. It just shifts from a highly efficient push model to a fallback pull model. This is the hallmark of enterprise-grade integration. You never assume the server supports optional features. You empirically verify it in the capabilities payload and branch your logic accordingly.
That branching logic is also deeply tied to the security posture of the application. We often think of capability negotiation as just feature discovery, but it is fundamentally a security boundary. When a server boots up and generates its capabilities object, it is defining its own attack surface. Let us say you deploy a microservice designed solely to expose internal company documentation to an AI agent. That server has no business executing system commands or modifying databases. Therefore, during the initialize phase, that server will output a capability object that only includes the resources property. It completely omits the tool's property. From a security perspective, what are the strict implications of that omission for both the client and the server's message router?
The security implications are absolute and non-negotiable. By omitting the tool's property from its capabilities object, the server has cryptographically, within the context of the protocol, declared that it does not implement tool execution. On the client side, a well-written client will read this capability object and immediately disable any user interface elements or internal routing paths related to tool execution for that specific server connection. The client should not even attempt to send a tools/call request. However, we cannot trust the client. A malicious, compromised, or simply buggy client might still formulate and transmit a JSON remote procedure call request invoking a tool. This is where the server's internal router must enforce the boundary negotiated during initialization. Because the tool's capability was not declared, the server's router must not pass that request down to any underlying business logic. It must intercept the request at the highest possible layer and instantly return an error object with a standard code indicating that the method is not found or the capability is not supported. This is a fail-close architecture. You do not leave unused endpoints open and rely on authentication to protect them. You prune the endpoints entirely based on the capability handshake. If a capability is not explicitly negotiated, any attempt to exercise it is treated as a protocol violation.
That fail-close mentality is exactly why this protocol is suitable for enterprise deployments. You are proactively reducing the footprint of potential vulnerabilities. Now, let us talk about the completion of this initialization phase. The client sends the initialize request, the server processes it, and sends back its server information and capabilities in the response. But the handshake is not actually over at that point, is it? There is a crucial third step required to finalize the connection state. The client has to send an initialized notification back to the server. Why is this three-way handshake necessary, and what is the exact state machine transition happening under the hood?
The three-way handshake is a brilliant design choice inherited from decades of network protocol engineering, specifically mirroring the transmission control protocol, but implemented here at the application layer. When the server sends its initialized response, it has told the client its capabilities, but the server does not actually know if the client received that response or if the client accepted the server's version and capabilities. If the server were to immediately start pushing notifications to the client at this point, those messages might be lost or the client might be in the middle of dropping the connection due to a version mismatch. Therefore, the server remains in a pending state. It is only when the client sends the initialized notification, which is a one-way message requiring no response, that the server officially transitions its internal state machine to fully connected. This initialized notification acts as the client's definitive statement saying, "I have received your capabilities, I am satisfied with the negotiation, and I am now ready to begin standard operations." Only after receiving this notification is the server permitted to send asynchronous notifications, such as a resource updated event or a prompt list changed event. If you are writing a server implementation and you start firing off notifications before you process that initialized message, you are breaking the protocol specification and causing race conditions in the client state manager.
It is a synchronized starting gun for the session. And speaking of extending that session beyond the standard specification, I want to dive into the experimental object within the capabilities payload. The protocol authors were wise enough to know they could not predict every future use case. Both the client capabilities and the server capabilities allow for an experimental property, which is essentially a free-form object where vendors can declare support for custom, non-standard features. How should engineers approach using the experimental capabilities, and what are the best practices for namespacing to avoid collisions if multiple vendors start introducing their own custom tools or resource types?
The experimental object is the designated escape hatch for innovation, but it is also a potential minefield if used recklessly. If you are building a proprietary feature that only your specific client and your specific server understand, you declare it inside the experimental object. However, you must namespace your keys to prevent catastrophic collisions. You should never use a generic key like advanced logging. Instead, you must use a reverse domain name notation or a highly specific vendor prefix, such as com.vinkius.advanced logging. During the handshake, the client sends its experimental capabilities and the server sends its own. The negotiation here is entirely custom. The client has to look for that specific namespaced key in the server's response. If it is there, the client can enable its proprietary features. If it is not, the client must fall back to the standard protocol specification. I have seen massive architectural failures where a development team heavily relied on an experimental capability for a core business function without writing a fallback path. When they tried to connect their client to a standard, open-source server, the client immediately crashed with a null pointer exception because it blindly assumed the experimental feature was negotiated. Experimental capabilities must always be treated as optional enhancements, never as guaranteed foundational requirements, unless you are strictly controlling both the client and the server environments.
That is a critical warning. The protocol is designed for interoperability, and hard-coding dependencies on experimental features destroys that interoperability. I want to shift our focus to the lifecycle management of these capabilities after the initial handshake. We established that the initialization phase sets the boundaries, but what happens if the underlying environment changes during a long-running session? Let us say a server dynamically loads a new plugin that grants it the ability to execute tools, but it originally booted up and initialized without the tool's capability. Can a server renegotiate its capabilities mid-session, or is that initial handshake permanently binding for the lifespan of that specific transport connection?
That is a profound architectural question. Under the current strict interpretation of the Model Context Protocol, the capabilities negotiated during the initialize handshake are permanently binding for the duration of that transport connection. There is no standard reinitialize or update capabilities request. If a server dynamically loads a new plugin that adds tool execution capabilities, it cannot suddenly start accepting tool call requests if it did not declare the tool's capability during the initial handshake. The client is already operating under the assumption that tools are unsupported. If the server wants to expose this new capability, the accepted pattern is to gracefully terminate the current connection and force the client to reconnect. When the client reconnects and sends a new initialize request, the server will then respond with its updated capability payload, including the newly loaded tools. This design might seem rigid, but it is purposefully chosen to guarantee state consistency. If capabilities could change arbitrarily mid-session, every single client request would have to be preceded by a capability check, adding immense latency and complexity. By locking the capabilities at initialization, the client can safely cache the server's feature set in memory and execute requests with zero validation overhead. It forces the complexity onto connection lifecycle management rather than per-request validation.
That makes perfect sense from a performance optimization standpoint. It is about front-loading the heavy lifting of state validation so that the actual data transmission remains incredibly fast and lean. It also emphasizes why error handling during the initialization phase must be bulletproof. If the transport layer drops right as the server sends the initialize response, but before the client can send the initialized notification, both sides are left in a hanging state. The client thinks the connection failed, but the server might think the connection is just heavily delayed. How should an engineer implement timeout and cleanup mechanics specifically around this handshake window to prevent memory leaks and zombie connections?
Handling partial handshakes requires aggressive timeout mechanisms. When the client transmits the initialize request, it must immediately start a high-resolution countdown timer. A standard acceptable threshold is typically 5 to 10 seconds, depending on the network topology. If the server's response is not received, fully parsed, and validated within that window, the client must aggressively tear down the transport layer, close the standard input-output streams, or sever the WebSocket, and throw a critical initialization timeout error to the application layer. The client cannot simply retry sending the initialize request on the same transport because the transport state is now compromised. On the server side, the logic is symmetrical. When the server accepts a transport connection and receives the initialize request, it sends its response and starts its own timer waiting for the client's initialized notification. If that notification does not arrive within the timeout window, the server must conclude that the client has died or disconnected ungracefully. The server must immediately terminate the transport connection, flush any allocated memory buffers for that session, and discard the pending state. You cannot allow uninitialized connections to linger in memory. They are prime targets for denial of service attacks. A malicious actor could open 10,000 WebSocket connections, send the initialize request, receive the response, and then intentionally withhold the initialized notification. If your server does not have a strict timeout cleanup routine, it will quickly exhaust its available memory, tracking thousands of ghost sessions.
That is a terrifying but incredibly realistic scenario, and it highlights why understanding the protocol at this low level is mandatory for certification and production deployment. You are not just writing code that works when everything goes right, you are engineering defensive systems that survive when everything goes wrong. Let us quickly summarize the capability negotiation before we transition to the actual transport implementations. The handshake is a three-step dance: client initialize request, server initialize response, and client initialize notification. The capabilities object dictates the strict functional boundaries, enabling dynamic feature toggling and fail-close security. Versioning is strict and negotiated upfront, and any unsupported experimental features must be handled with graceful degradation. And finally, the negotiated state is immutable for the lifespan of the connection, requiring a full reconnect if the underlying capabilities change. This is the bedrock of the protocol. If you get this wrong, everything built on top of it will eventually collapse.
Precisely. You have perfectly encapsulated the initialization architecture. You now possess the blueprint for how these AI systems introduce themselves and establish the rules of engagement. But all of this intricate negotiation is just theoretical data structures until we actually push those bytes across a physical boundary. We have defined the payload, we have defined the rules, and now we must define the vehicle. It is time to roll up our sleeves and look at the actual transport layers that carry these messages. We are going to start with the most fundamental, performant, and deeply integrated transport available in the protocol, the standard input and standard output transport layer. This is where we move away from network sockets and dive directly into operating system process management. Transitioning from our previous point regarding architectural boundaries, we need to dissect the STDIO transport layer within the Model Context Protocol. When we analyze the transport mechanisms available in MCP, the standard input and standard output streams provide a profoundly different operational paradigm compared to server-sent events or WebSockets. Maya, how does the STDIO transport fundamentally alter the client-server interaction model in the context of local AI tool execution?
The STDIO transport fundamentally shifts the paradigm from a network-bound, asynchronous communication model to a strictly localized, process-based inter-process communication mechanism. Instead of opening a TCP socket and dealing with network latency, packet loss, or TLS overhead, the MCP client spawns the MCP server as a direct child process. The communication then flows entirely through the standard input and standard output streams of that child process. This means the client writes JSON RPC messages directly to the server's STIN buffer, and it reads the server's responses directly from its stout buffer. It heavily borrows from the architectural decisions made in the Language Server Protocol, or LSP. The consequence is near zero latency communication, but it introduces significant complexities regarding stream management, message framing, and process lifecycle synchronization.
That is a critical distinction. The reliance on standard streams means we lose the inherent message boundaries provided by HTTP or WebSockets. In a continuous byte stream, how does MCP ensure that a JSON RPC payload is correctly delineated? Without a robust framing protocol, a fragmented read could lead to catastrophic JSON parsing errors, effectively breaking the state machine of the protocol.
Precisely. To solve the boundary problem, the STDIO transport layer employs a very specific framing mechanism. While the base JSON RPC 2.0 specification does not mandate a transport protocol, when transmitted over STDIO, it requires a mechanism to denote the start and end of a message. Often, implementations utilize a header-based approach, similar to HTTP but stripped down. We typically see a content-length header followed by a carriage return and line feed pair, and then the actual JSON payload. For instance, the client reads the incoming bytes until it encounters the double CRLF sequence, parses the content-length integer, and then reads exactly that number of bytes from the stream. This deterministic byte counting is crucial because it allows the receiver to handle fragmented chunks across multiple operating system ticks without attempting to prematurely parse incomplete JSON structures.
The content-length framing is robust, but it places a strict requirement on the buffer management of both the client and the server. Let us consider the scenario where the AI model generates a massive payload, perhaps a very large context retrieval from a local database tool. If the server writes this multi-megabyte JSON payload to Stout, and the client's internal read buffer is significantly smaller, say 64 kilobytes, the client must reconstruct the message across dozens or hundreds of read events. How does the MCP STDIO implementation typically handle backpressure and memory allocation in these high-throughput scenarios?
Backpressure handling in STDIO is entirely dependent on the underlying operating system's pipe implementation and the runtime's asynchronous I/O primitives. When the server writes to Stout, it is writing to an OS-level pipe. If the client is slow to read from its end of the pipe's internal buffer, typically 64 kilobytes on Linux, fills up. Once full, any subsequent write operations by the server will block or yield if using non-blocking I/O until the client consumes some bytes. From the client's perspective, memory allocation strategies become paramount. A naive implementation might allocate a dynamically growing array or string, constantly copying memory as new chunks arrive. A high-performance MCP client, however, will pre-allocate a buffer exactly matching the parsed content length and then perform zero-copy reads or direct memory mapping into that contiguous block. This prevents heap fragmentation and minimizes garbage collection overhead in managed languages like Node.js or Python, which is vital when processing gigabytes of tokenized context.
That blocking behavior you mentioned introduces a potential deadlock scenario. If the client sends a massive request to the server via STIN, and simultaneously the server is trying to send a massive asynchronous notification to the client via Stout, and both OS pipe buffers fill up, both processes could block indefinitely, waiting for the other to read. How does the protocol architecture mitigate these bidirectional I/O deadlocks?
The deadlock scenario you described is a classic problem in bidirectional IPC. To mitigate this, robust MCP STDIO implementations mandate fully asynchronous, non-blocking I/O architectures. Neither the client nor the server should ever perform a synchronous, blocking read or write operation on the standard streams. Instead, they must rely on event loops or async/await state machines. In Rust, this means using Tokyo's asynchronous process and I/O modules. In Node.js, it means utilizing the event-driven stream API. In Python, it requires Asyncio and non-blocking file descriptors. Furthermore, dedicated background threads or green threads are often employed strictly for pumping data into and out of the I/O streams. These threads read from the OS pipe as fast as possible, pushing the raw bytes into unbounded or gracefully degrading internal queues, decoupling the stream reading from the actual JSON RPC parsing and business logic execution. This ensures the OS pipes remain clear, preventing the mutual blocking state.
Shifting focus to the execution environment, utilizing SDDIO inherently means the MCP client must have the capability and permissions to spawn arbitrary executables. The client must execute a command, say, a Python interpreter pointing to an MCP server script, or a compiled Go binary. This creates a fascinating security perimeter. Unlike an HTTP endpoint where the server is an isolated entity on the network, the SDDIO server runs with the same, or derived, user permissions as the client process. What are the security implications of this local execution model?
The security perimeter in the SDDIO model is indeed radically compressed. When an MCP client, perhaps an IDE plugin or a local desktop application, spawns an MCP server, that child process inherits the user identifier, group identifier, and potentially the environment variables of the parent. If a malicious or compromised AI model tricks the client into executing a vulnerable tool on the local server, the blast radius is the user's entire local file system and network access. Therefore, sandboxing becomes a critical architectural requirement. In advanced deployments, we do not simply execute the raw binary. We wrap the child process spawn command in a virtualization or containerization layer. For instance, the client might invoke a Docker container or use namespaces and groups on Linux, like the brap utility, mapping only the necessary input-output streams to the container's standard streams. This restricts the MCP server's view of the file system to a specific directory and completely disables its network stack, enforcing the principle of least privilege while still utilizing the zero-latency SDDIO transport.
The containerization approach solves many security concerns, but it introduces complications regarding environment variable inheritance and working directories. Often, local tools need access to user-specific configurations, like AWS credentials or local SSH keys, to perform their designated tasks. If we sandbox the SDDIO process, we must explicitly inject these secrets. How does the Model Context Protocol specify or recommend handling authentication and authorization for tools running over local SDDIO?
Interestingly, the core Model Context Protocol specification explicitly avoids dictating authentication mechanisms for the SDDIO transport. It treats SDDIO as an implicitly trusted channel because the creation of the channel itself requires localized operating system privileges. The assumption is that if you can spawn the process, you are already authorized. However, from an implementation standpoint, we heavily utilize initialization parameters. When the client sends the initial JSON RPC initialize request over the established SDDIO stream, the payload can include specific authentication tokens, capability negotiations, and explicit configuration mappings. Instead of relying on inherited environment variables, which can be leaky and insecure, the client explicitly passes structured configuration data during the handshake phase. The server then uses this bounded configuration. Furthermore, standard error, or STAIR, plays a crucial role here. STAIR is not used for the protocol framing. It is reserved entirely for out-of-band logging. If an authorization failure occurs during initialization, the server can dump detailed diagnostic telemetry to STAIR before cleanly terminating the stout connection, allowing the client to separate protocol errors from application-level security violations.
The distinction between stout for protocol transport and STAIR for out-of-band telemetry is a highly effective design pattern. It prevents log pollution from corrupting the JSON RPC message framing. However, let us examine the termination and lifecycle management of these child processes. When the MCP client decides it no longer needs the server, or if the client crashes unexpectedly, we risk creating zombie processes or orphan children consuming system resources indefinitely. What are the architectural safeguards to ensure deterministic process termination in the SDDIO model?
Deterministic termination in a child process model is notoriously difficult across different operating systems. The standard graceful shutdown sequence involves the client sending a JSON RPC exit notification. Upon receiving this, the MCP server is responsible for releasing any held resources, flushing its final logs to stare, closing its end of the standard streams, and exiting with a status code of 0. The client waits for the pipe closure and reaps the child process. However, if the client crashes abruptly, it cannot send the exit notification. To handle this, the server implementation must actively monitor the state of its STIN stream. When the parent process terminates, the operating system will automatically close the right end of the pipe. The server's subsequent read operation on STIN will encounter an end-of-file or EOF signal. A robust MCP server must interpret an unexpected EOF on STIN as a mandatory termination signal and initiate an immediate, albeit potentially ungraceful, shutdown.
That covers the Unix-like systems reasonably well, but we must consider cross-platform compatibility, particularly Windows. The behavior of standard input pipes and process trees on Windows NT differs significantly from POSIX standards. An EOF on STIN might not be reliably delivered under all crash conditions, especially if the client is forcefully terminated via the task manager. Do we need secondary heartbeat mechanisms or operating system-specific watchdogs to guarantee process cleanup on Windows?
Cross-platform compatibility is the bane of IPC architecture. You are absolutely correct that Windows handles pipe closures and process groups differently. While an EOF on STIN is generally reliable if the parent crashes normally, a hard termination might leave the pipe in an indeterminate state, or the child might be blocked on a system call that ignores the pipe state. To guarantee cleanup, advanced MCP implementations often utilize a combination of techniques. One approach is a bidirectional heartbeat implemented over the JSON RPC channel itself, though this introduces overhead. A more efficient, OS-level approach on Windows involves using job objects. When the client spawns the server, it assigns the child process to a Windows job object. The client configures the job object to automatically terminate all associated processes when the last handle to the job is closed. If the client crashes, the OS closes the handle, and the kernel forcibly terminates the MCP server, providing a robust, zero-overhead guarantee against orphan processes, bypassing the vagaries of stream state entirely.
Using Windows job objects is a highly optimized solution for resource management. Let us pivot to the developer experience and observability. Debugging a network-based protocol like HTTP is straightforward. You can use tools like Wireshark or a proxy like Charles to inspect the traffic. But debugging an SDDIO-based protocol is inherently opaque because the communication happens in memory buffers between a parent and child process. How do we instrument and monitor the JSON RPC traffic flowing over these standard streams without interfering with the tightly coupled stream lifecycle we just discussed?
Observability in an SDDO environment requires the implementation of an interceptor or a proxy process. You cannot easily attach a sniffer to an anonymous OS pipe. Instead, the developer modifies the client configuration to spawn a debugging proxy instead of the actual MCP server. This proxy process acts as a transparent relay. It accepts the client's STIN, duplicates the byte stream, writes one copy to a log file or a local monitoring dashboard, and forwards the other copy to the actual MCP server, which it spawns as its own child. It performs the same duplication for the server's stout, relaying it back to the client. This technique, often called a T-proxy, allows full introspection of the binary payload, message framing, and JSON RPC structure without altering the client or server code. Furthermore, sophisticated proxies can validate the JSON schema in real time, instantly flagging malformed requests or responses that deviate from the model context protocol specification, drastically reducing the time required to isolate parsing bugs.
The proxy approach is elegant. It essentially recreates the man-in-the-middle capability we rely on in network debugging. But this brings us to a critical performance consideration: latency. The primary argument for using SDDIO over local HTTP or WebSockets is the reduction of latency. However, if we introduce framing layers, content length parsing, and potentially asynchronous queuing within both the client and server processes, do we actually achieve a meaningful latency reduction compared to simply using the loopback network interface?
The latency argument requires careful empirical analysis. In a local loopback scenario, TCP overhead is indeed minimized by the OS kernel, often bypassing the physical network stack entirely. However, HTTP introduces substantial parsing overhead for headers, method verbs, and URL routing on every single request. WebSockets reduce this after the initial handshake, providing a persistent framing layer similar to our SDDIO implementation. Where SDDIO definitively wins is in the elimination of socket allocation, port exhaustion issues, and the complete bypass of the network namespace. Furthermore, the context switching overhead is marginally lower. Pushing thousands of small JSON RPC tool invocation requests per second, the SDDIO transport consistently exhibited lower tail latency and significantly reduced CPU utilization compared to local WebSockets. The cost of parsing the simple content length header is negligible compared to the overhead of a full HTTP parser or the masking requirements of the WebSocket protocol. The performance delta becomes especially pronounced when the AI model is streaming massive, multi-megabyte tensor representations or complex AST structures directly through the local pipe.
Speaking of streaming complex structures, the Model Context Protocol heavily utilizes the concept of pagination and progressive data delivery. When an AI model requests a massive directory tree or a huge database table via an MCP tool, the server cannot realistically load the entire dataset into memory, serialize it into a single JSON monolith, and push it over stout. How does the SDDIO transport handle stream multiplexing or interleaved responses to support these progressive data transfers without blocking concurrent tool requests?
That touches on the limitations of a single, bidirectional pipe. SDDIO does not natively support multiplexing. It is a strictly serial stream of bytes. If the server is writing a 1 GB JSON response for tool A and the client sends a fast, lightweight request for tool B, tool B's response will be blocked behind the massive payload of tool A. To solve this, the MCP specification relies on the asynchronous nature of JSON RPC notifications and server-sent events, conceptually mapped over the JSON RPC structure. Instead of returning the massive payload in the direct response to tool A's request, the server immediately returns a lightweight response containing a pagination cursor or an async task identifier. Then, as the server progressively loads the data, it emits a sequence of JSON RPC notifications back to the client, tagging each payload with that identifier. Because these notifications are independent JSON objects, the server can interleave them with the responses to tool B. The client's parser simply reconstructs the data stream based on the identifiers. This pushes the complexity of multiplexing up to the application layer, keeping the SDDIO transport layer remarkably simple and focused purely on sequential byte delivery.
That architectural decision to enforce application layer multiplexing aligns perfectly with the Unix philosophy of doing one thing well. The transport simply moves bytes. The protocol manages the state. Let us explore the implications of this for language-specific implementations. Writing a highly concurrent, asynchronous MCP server in Rust utilizing Tokio is structurally distinct from writing one in Python using Essentio, particularly regarding how they interface with the underlying C library's standard streams. What are the specific pitfalls developers encounter when implementing the SDDIO transport in Python?
Python presents unique challenges for high-throughput SDDIO due to the global interpreter lock, or GL, and the historical design of its sys.stin and sys.stat objects. By default, these file objects in Python are often line buffered or block buffered, and they are inherently synchronous. If you attempt to read from sys.stin using a simple read, call, and no data is available, the entire Python thread blocks. This violates our non-blocking requirement. To implement a robust MCP server in Python, you must bypass the high-level sys objects entirely. Developers must drop down to the OS-level file descriptors, using os.read and os.write, and configure them for non-blocking operations using the fcntl module on Unix systems. Furthermore, integrating these non-blocking file descriptors with the Essentio event loop requires registering them with the loop's internal EPOL or queue mechanisms using loop.add_reader and loop.add_writer. Failure to do this correctly results in CPU spinning, where the server constantly pulls the empty pipe, consuming 100% of a core, or deadlocks where the essentio loop is stalled by a blocking red. It requires a deep understanding of asynchronous I/O primitives that many high-level Python developers are not accustomed to.
That is a critical point of failure. The abstraction leakage in Python stream handling can severely impact the reliability of the AI toolchain. Conversely, Node.js was designed from its inception around asynchronous I/O. Does the V8 engine and the lib event loop in Node.js provide a significantly smoother developer experience for implementing the MCP STDIO transport layer?
The developer experience in Node.js is demonstrably superior for this specific architecture. Node's process.stin and process.stout are inherently asynchronous streams backed by libof. You simply attach a data event listener to process.stin, and the runtime automatically handles the EPL notification, memory allocation for the chunk, and dispatches the callback on the main event loop without any risk of blocking. You can pipe these streams directly into transform streams that handle the content length buffering and JSON parsing natively. The backpressure mechanism is also built in. If you call process.stout.write and the OS pipe is full, it returns false, and you can listen for the drain event to resume writing. This tight integration means a fully compliant, highly performant MCP STDIO transport can be implemented in Node.js in a fraction of the lines of code required in Python or even Rust, making it the de facto standard for rapidly prototyping and deploying local AI tools within our ecosystem.
The efficiency of Node.js in this domain is undeniable. However, when we consider the deployment of these tools to end users, requiring a Node.js runtime to be installed locally presents a distribution hurdle. This brings us back to compiled languages like Rust or Go. While the implementation complexity is higher, shipping a single, statically linked binary as an MCP server offers a frictionless installation process. How does the static compilation strategy affect the architecture of the STDIO transport, particularly regarding dynamic tool loading?
The static binary approach fundamentally alters the extensibility model. In a Node.js or Python environment, the MCP server can dynamically load new tools at runtime by importing scripts or modules from the file system. With a statically compiled binary in Go or Rust, the tool logic is baked into the executable. If the user wants to add a new tool, they must download a newly compiled binary. To mitigate this rigidity while maintaining the deployment benefits, advanced architectures use a hybrid approach. The statically compiled binary acts as a primary MCP router and STDIO transport handler. When a request for an unknown tool arrives, this router can, in turn, spawn secondary child processes, perhaps lightweight shell scripts, WebAssembly modules, or other binaries, and route the JSON RPC calls to them using further nested STDIO connections or local named pipes. The primary binary manages the complex framing, backpressure, and error handling of the main connection to the AI client, while delegating the specific business logic to modular, hot-swappable plugins.
A hierarchical process topology utilizing nested STDIO transports is a fascinating architectural pattern. It effectively creates a microservices architecture confined entirely within the local machine's process tree. This model, however, amplifies the observability challenges we discussed earlier. Tracing a single JSON RPC request from the client through the primary router and down into a secondary plugin process requires rigorous context propagation. How does the model context protocol specification address distributed tracing within this localized environment?
The MCP specification acknowledges this complexity by supporting standard telemetry and tracing paradigms. Specifically, it encourages the use of JSON RPC metadata to inject trace context, similar to the W3C trace context standard used in HTTP headers. When the client initiates a request, it generates a trace ID and a span ID, embedding them within the JSON RPC request object, often within a dedicated metadata or context field. The primary router reads this trace context. When the router delegates the task to a secondary plugin process via a nested STDIO stream, it must serialize and propagate that exact trace context into the new JSON RPC request. Furthermore, because we rely heavily on STAIR for out-of-band logging, every log line emitted by the router and the plugin should be structured, typically as JSON, and tagged with this trace ID. This allows an external log aggregation tool, running either locally or in the cloud, to ingest the disparate STAIR streams from the entire process tree and perfectly reconstruct the causal chain of events, providing full visibility into the localized microservice architecture.
The structured logging via STAIR combined with trace context propagation provides a complete observability solution. Let us consider the edge cases of error propagation. If the secondary plugin process encounters a fatal error, such as a segmentation fault or an out-of-memory exception, it will abruptly terminate, breaking the nested SDDIO pipe. The primary router will receive an EOF. How should the primary router encapsulate this catastrophic failure and communicate it back up the main SDDIO pipe to the AI client without destabilizing the primary connection?
Handling unexpected child process termination is a critical resilience requirement. When the primary router detects the EOF from the plugin, it must instantly transition into an error recovery state. It cannot simply forward the EOF to the client, as that would signal the termination of the entire MCP session. Instead, the router must synthesize a definitive JSON RPC error response. It constructs a message mapping to the original request ID that triggered the plugin, populating the error object with a specific error code, perhaps defined as an internal error or a custom tool execution failure. Crucially, the router must attempt to harvest any final telemetry from the plugin's STAIR buffer before the process was reaped. It can embed this final diagnostic output into the data field of the JSON RPC error object. The router then serializes this structured error and writes it to the main stout pipe. This elegant encapsulation ensures the AI client receives a deterministic, actionable error regarding the specific tool invocation, while the primary SDDIO transport remains stable and ready to process subsequent requests.
Synthesizing the error response ensures protocol stability. But what happens when the transport layer itself is compromised? Suppose a rogue tool attempts to write raw, unstructured binary data directly to the stout stream, completely shattering the JSON RPC framing and content length expectations. When the client attempts to parse this corrupted stream, it will encounter invalid header formats or malformed JSON. Is there a defined recovery protocol for stream desynchronization, or is the connection fundamentally unrecoverable?
In the event of catastrophic stream desynchronization, the connection is, for all practical purposes, unrecoverable. The SDDIO transport relies on strict byte alignment. If the client reads a content length header, expects 500 bytes of JSON, but instead receives 500 bytes of raw image data followed by fragmented JSON, the parser's state machine is permanently corrupted. There is no reliable mechanism to scan forward in the stream to find the next valid header sequence, because the binary data might coincidentally contain byte sequences resembling valid headers. Therefore, the standard operating procedure is immediate connection termination. The client must emit a fatal error log, explicitly close its right end of the pipe, and forcefully terminate the server process. It must then initiate a completely new spawn sequence to restart the MCP server from a clean state. This highlights why this segregation of protocol data on stout and arbitrary telemetry on STAIR is an absolute architectural mandate. Any leakage of unstructured data onto stout destroys the transport.
The fragility of the byte alignment reinforces the need for strict isolation and rigorous tool validation. Let us explore the initialization handshake in more detail. When the SDDIO pipe is first established, both the client and server are essentially blind to each other's capabilities. They must negotiate protocol versions, supported features, and tool registries before any actual work can commence. How does the initialization phase over SDDIO differ from a connection-oriented protocol like WebSockets?
The initialization phase over SDDIO is remarkably similar to WebSockets in structure, but it lacks the out-of-band metadata exchange provided by HTTP headers during the WebSocket upgrade request. In a WebSocket connection, you can pass authentication tokens or capability flags in the initial HTTP GET request. In SDDIO, you have only the raw byte stream from the moment the process starts. Therefore, the entire negotiation must occur within the JSON RPC payload itself. The client is obligated to send an initialize request as the very first message. This request contains the client's supported protocol version, its capabilities such as support for pagination, progress notifications, or specific payload encodings, and crucial contextual information about the environment. The server must hold all other requests in a pending state until it successfully processes this initialize request. It then responds with its own capability matrix, detailing the tools it provides, its support for resources, and any specific configuration requirements. Only after this synchronous, blocking handshake is complete does the protocol transition into its asynchronous, bidirectional operational phase.
That initial synchronous lock is essential for establishing the protocol baseline. It ensures both parties agree on the dialect they are speaking. Let us consider the scenario where the server needs to push real-time updates to the client without a preceding request. For example, a local build tool running via MCP wants to stream compilation progress back to the AI model. Since SDDIO does not have the concept of independent channels or topics, how are these asynchronous server-sent notifications structured within the raw byte stream?
Asynchronous notifications are handled seamlessly by the core JSON RPC 2.0 specification. A notification is simply a JSON RPC message that contains a method and params, but explicitly omits the ID field. Because the SDDIO transport layer treats all messages uniformly, wrapping them in the content length headers regardless of their type, the server can spontaneously inject these notification payloads into the stout stream at any time. The client's parser constantly reads the stream, strips the headers, parses the JSON, and inspects the resulting object. If it lacks an ID, the client's internal router dispatches it as an event rather than a response to a pending promise. This allows the server to emit continuous streams of telemetry, progress updates, or log events over the same unified pipe. The only constraint, as we discussed earlier, is that these notifications must be serialized and interleaved correctly with any ongoing response payloads to avoid fragmenting individual JSON objects.
The structural simplicity of omitting the ID field to denote an event is a powerful design choice. It keeps the parser logic unified. However, this unified stream architecture places a heavy burden on the client's event loop. If a server is hyperactive, flooding the stout stream with thousands of progress notifications per second, it could potentially starve the client's main thread, preventing it from parsing critical tool responses or processing user input. How does a robust client implementation manage backpressure against a noisy server?
Managing backpressure against a noisy server in a single-pipe architecture requires aggressive buffering and potentially message conflation at the client level. If the server is emitting progress updates at a rate of 1000 Hz, but the AI model's context window or the user interface can only refresh at 60 Hz, processing every single notification is computationally wasteful. A sophisticated MCP client will implement a throttling or debouncing layer immediately after the JSON parser. When it identifies an incoming notification, say a build progress event, instead of immediately dispatching it to the main application logic, it updates a localized state object representing the current progress. It then uses a timer to periodically flush the latest state to the application. Furthermore, if the OS pipe buffer begins to fill because the client is intentionally slowing down its read loop to shed load, the backpressure naturally propagates back to the server. The server's write operations will begin to yield, naturally throttling its emission rate to match the client's consumption capacity, leveraging the fundamental physics of the operating system pipe.
That natural propagation of backpressure through the OS pipe is precisely why SDDIO is such an elegant solution for local communication. It uses the operating system's native flow control mechanisms instead of requiring complex protocol-level windowing algorithms like TCP. As we wrap up this deep dive into the transport layer, let's look toward the future. The current implementation relies heavily on raw byte streams and JSON serialization. Are there emerging specifications or experimental transport layers within the model context protocol ecosystem that look to replace or enhance the traditional SDDIO approach, perhaps leveraging shared memory or binary serialization formats like flat buffers or protobuf?
The evolution of the transport layer is an area of intense research. While JSON RPC over SDDIO is the universal baseline, its serialization overhead becomes a bottleneck for high-bandwidth data transfers, such as passing raw video frames, large audio buffers, or uncompressed vector embeddings between the AI model and the local tool. There are active proposals to integrate out-of-band binary transfers. Instead of base 64, encoding a 50 megabyte image and stuffing it into a JSON string, which inflates the payload size by 33% and consumes massive CPU cycles. The JSON payload would merely contain a pointer or a handle to a shared memory segment. The client and server, running on the same physical machine, could then use POSIX shared memory or memory-mapped files to instantly access the binary data with zero copy overhead. Furthermore, replacing the JSON RPC payload entirely with a compact binary format like MessagePack or gRPC over Unix domain sockets is heavily debated. However, these optimizations trade the universal simplicity and debuggability of JSON over SDDIO for raw performance, introducing complex platform dependencies. For the foreseeable future, the standard content-length framed JSON stream will remain the robust, foundational transport layer for the Model Context Protocol.
The trade-off between human readability and machine efficiency is the eternal struggle in protocol design. The elegance of the current SDDIO implementation lies in its accessibility. Any developer can build an MCP server in an afternoon using standard libraries available in almost every programming language. The deep architectural nuances we've discussed today, process lifecycle management, stream isolation, backpressure handling, and cross-platform synchronization, are the hidden complexities that make this seemingly simple pipe so powerful in practice.
Exactly. By mastering the intricacies of the SDDIO transport layer, developers can build highly resilient, zero-latency local toolchains that seamlessly extend the capabilities of large language models, pushing the boundaries of what is possible with localized AI architectures. Understanding the raw byte flow is the first step toward building truly autonomous, secure, and performant agentic systems.
An excellent summary. We have thoroughly disassembled the mechanics of the Model Context Protocol's SDDIO transport. In our next segment, we will pivot to the structural schemas and semantic boundaries that define the tool definitions themselves, exploring how the AI model discovers and reasons about the capabilities exposed over these local streams.
Actually, before we completely close the book on the transport layer and transition into those semantic boundaries, there is a massive architectural gap we need to cross. We have spent an incredible amount of time dissecting the standard input and output streams, which, as we established, are absolutely perfect for local, co-located processes. But the reality of modern enterprise infrastructure is that the artificial intelligence model and the tools it needs to access are very rarely sitting on the same physical machine or even within the same containerized environment. When you start building distributed agentic systems, you immediately hit the limitations of process-based communication. You cannot pipe standard output across the public internet or across different availability zones in a cloud environment. This is exactly where the Model Context Protocol defines its secondary, yet equally critical, transport mechanism, which relies on standard HTTP and server-sent events. The shift from a local, persistently connected pipe to a remote, inherently stateless network boundary fundamentally changes how we must think about connection life cycles, message routing, and overall system resilience. If you are preparing for the certification exam, understanding the precise mechanics of the HTTP and SSE transport is not just optional, it is a core requirement because it is the backbone of any remote tool integration. We need to unpack why the protocol designers chose server-sent events over other bidirectional network protocols like WebSockets, and how they managed to simulate a persistent, bidirectional communication channel using what are essentially two separate, asynchronous pathways.
That is a crucial pivot, Maya, and it perfectly sets the stage for the realities of enterprise-scale deployments. You are entirely correct that the local process boundary is a luxury we often do not have. When we move to networked communication, the Model Context Protocol could have adopted any number of established patterns. They could have mandated WebSockets, which provide a true full duplex, persistent connection over a single TCP socket. They could have opted for gRPC, leveraging HTTP/2 streams and protocol buffers for highly optimized binary transport. However, the architectural decision to utilize server-send events for server-to-client communication paired with standard HTTP post requests for client-to-server communication is a masterclass in pragmatic protocol design. Let us break down exactly how this works under the hood. A server-send event stream is a unidirectional channel where a client initiates an HTTP GET request to a specific endpoint, and the server responds with a special content type, specifically text/event stream. The server holds this HTTP response open indefinitely, continuously pushing discrete text-based events down the wire to the client. This solves the problem of how the server, which in the context of MCP is the tool provider, can asynchronously push notifications, telemetry, or long-running task updates back to the client, which is the AI model or the orchestrator. But SSE is strictly one way. To achieve the bidirectional flow required by the JSON RPC messages of the Model Context Protocol, the client must use a completely separate mechanism to send its commands to the server. This is where standard HTTP post requests come into play. Every time the client needs to invoke a tool, request a capability, or send a ping, it fires off a distinct HTTP post request to a complementary endpoint on the server. The payload of this post request is the exact same JSON RPC message structure we saw in the standard input transport. The profound implication here is that the protocol deliberately decouples the incoming command channel from the outgoing event channel. This separation of concerns allows the HTTP infrastructure to behave exactly as it was designed to. You can cache, proxy, and load balance the post requests using standard web application firewalls and ingress controllers, while the SSE stream maintains a lightweight, persistent funnel for asynchronous server responses.
The decoupling of the channels is indeed a brilliant architectural choice, but it immediately introduces a significant state management problem that local standard streams never have to deal with. When you are piping standard input to a child process, the operating system kernel guarantees that the file descriptors belong to that specific process pair. There is an implicit, unbreakable session identity. But over a network, HTTP is stateless. If a client is firing post requests to an endpoint and the server is streaming responses down an open SSE connection, how does the server know which post request belongs to which SSE stream? The Model Context Protocol solves this by introducing explicit session initialization and routing identifiers. When the client first connects to the server to establish the transport, it hits an initialization endpoint. The server accepts the connection, upgrades it to an SSE stream, and the very first event it pushes down that stream contains a unique session identifier, often structured as a UUID or a cryptographically secure token, along with the specific base URL that the client must use for all subsequent post requests. This means the server dynamically provisions the command channel URL based on the established event channel. From that moment on, every time the client wants to send a JSON RPC message, it must append this session identifier to the post request, either as a path parameter, a query string, or a specific HTTP header, depending on the exact implementation details of the server. This allows the server-side router to receive an incoming post, extract the session identifier, look up the corresponding active SSE stream in its internal state memory, execute the requested tool, and then route the JSON RPC response back down the correct SSE pipe. It is a manually constructed full duplex session layered over disparate HTTP primitives. And because you are dealing with the chaotic nature of the network, you have to engineer for failure. Networks drop packets, load balancers aggressively terminate idle connections, and mobile clients switch cell towers. The resilience of this transport layer relies heavily on the native recovery mechanisms built into server-sent events, specifically the last event ID header, which allows the client to explicitly tell the server exactly which message it received last before the connection dropped.
The elegance of the last event ID mechanism cannot be overstated, especially when you are designing systems that must guarantee at least once or exactly once delivery semantics for tool executions. Let us dissect that reconnection lifecycle because it is a frequent trap for engineers new to the protocol and a guaranteed topic on the certification exam. When the server pushes an event down the SSE stream, it can optionally prefix the payload with an ID field. This is not the JSON RPC message ID. This is a sequential or unique transport level identifier for the event itself. The client HTTP library automatically tracks the highest ID it has successfully received. If an intermediary proxy severs the TCP connection due to a timeout, the client does not just blindly reconnect and hope for the best. Instead, it issues a new HTTP GET request to re-establish the SSE stream. But this time, it injects the last event ID header containing that tracked value. The server intercepts this header, consults its own message buffer, and immediately replays any events that were dispatched after that specific ID before resuming the live stream. This prevents the catastrophic scenario where an AI model commands a tool to execute a critical database mutation. The network blips, the tool completes the mutation and sends the success response, but the response is lost in the void. Without event replay, the model would eventually time out, assume the tool failed, and potentially retry the operation, leading to corrupted state or unintended side effects. Of course, this implies that the server must maintain a ring buffer or an in-memory queue of recent outbound messages for every active session, which introduces memory overhead that you must account for in your capacity planning. You also have to implement intelligent backoff and jitter on the client side during these reconnections to prevent a thundering herd scenario where a brief network partition causes thousands of disconnected clients to simultaneously hammer the server with reconnection requests, effectively executing a self-inflicted denial of service attack. Network resilience is not just about retrying. It is about retrying responsibly.
Building on that concept of responsible and resilient architecture, we absolutely must dive into the security considerations of moving the model context protocol from a local process boundary to a remote network boundary. When we were discussing the standard input and output transport, the security perimeter was essentially defined by the operating system user permissions and process isolation. If a malicious actor compromised the local machine to the point where they could inject data into the standard input stream, you already had a catastrophic system-level breach. But the moment you expose an MCP server over an HTTP interface, your attack surface expands exponentially. You are now listening on a network port, potentially exposed to internal corporate networks or even the public internet. The baseline requirement for any HTTP-based MCP transport is Transport Layer Security, or TLS. You must encrypt the data in transit to prevent man-in-the-middle attacks from intercepting the raw JSON RPC payloads, which could contain highly sensitive prompts, API keys, or proprietary data retrieved by the local tools. But encryption is just the first layer. You must implement robust authentication and authorization. Because the protocol decouples the initialization GET request from the subsequent POST requests, your authentication mechanism must secure both endpoints consistently. The most common pattern is to leverage standard HTTP authorization headers using bearer tokens, such as JSON Web Tokens or JWDs. The client injects the token into the headers of the initial SSE connection request, and the server validates the signature and expiration before upgrading the connection. Crucially, the client must also inject this identical token into every single POST request it sends. If you only secure the initial connection but leave the POST endpoint open, an attacker could blindly fire JSON RPC commands at your server, guessing session IDs or simply overloading the parsing engine. Furthermore, because MCP servers often bridge the gap between AI models and critical backend systems, you should strongly consider implementing mutual TLS, where the server also cryptographically verifies the identity of the client via a client-side certificate. This provides a zero-trust architecture that is far more robust than simple bearer tokens, especially in highly regulated environments like finance or healthcare.
Those security primitives are non-negotiable, and they tie directly into how you deploy these servers in a production environment. You are rarely going to expose the raw Node.js or Python MCP server directly to the network. Instead, you will place it behind an API gateway or a reverse proxy like Nginx or Envoy. This is where the choice of HTTP and SSE really shines compared to WebSockets. Reverse proxies have decades of optimization for handling stateless POST requests and long-lived HTTP downloads, which is essentially what an SSE stream is. However, you have to carefully configure your proxy settings. Many load balancers are configured by default to aggressively buffer HTTP responses until they reach a certain size before flushing them to the client, which is disastrous for an event stream because it introduces artificial latency. You must explicitly configure your proxy to disable proxy buffering for the SSE endpoints and ensure that it supports chunk transfer encoding. Additionally, you need to implement strict rate limiting on the post endpoint to mitigate brute force attacks and prevent a rogue or hallucinating AI model from entering an infinite loop and flooding your infrastructure with tool invocation commands. You also need to configure aggressive timeouts for the post requests while allowing infinite or very long timeouts for the SSE connection. This dichotomy of timeout profiles is a unique operational challenge of the HTTP transport layer. When you look at the entire landscape, you start to realize that running an MCP server over a network requires a dedicated infrastructure strategy. You are not just deploying a script, you are deploying a highly available, secure, stateful routing component that acts as the absolute gatekeeper between advanced cognitive models and your proprietary enterprise data.
This brings us to a perfect juncture for a comprehensive architecture review of the Model Context Protocol transports, consolidating everything we have covered into actionable architectural principles. The fundamental decision you must make when designing an MCP integration is selecting the appropriate transport layer, and that choice dictates the entire trajectory of your system architecture. If you are building a local desktop application, an integrated development environment plugin, or a tightly coupled microservice where the orchestrator and the tools run on the same virtual machine, the standard input and output transport is your undisputed champion. It offers zero network latency, trivial security boundaries enforced by the operating system, and absolute simplicity in deployment. You launch a child process, hook into its standard streams, and you are immediately speaking the protocol. There are no dropped packets, no reconnect logic, and no complex session management. However, this tight coupling fundamentally limits your ability to scale horizontally or share tools across multiple disparate AI agents. The moment you need to decouple the lifecycle of the AI model from the lifecycle of the tools, or the moment you need to centralize access to secure backend systems, you must transition to the HTTP and server-sent events transport. This remote transport unlocks distributed architectures, allowing a single high-powered AI model sitting in a cloud data center to interact securely with a fleet of lightweight MCP servers deployed across edge devices, on-premises networks, or different cloud providers. But as we have explored in deep detail, this flexibility comes with the massive operational tax of managing network state, engineering for resilience, implementing robust cryptographic security, and tuning complex reverse proxy infrastructure.
Exactly. The HTTP and SSE transport is the bridge that allows the Model Context Protocol to scale from a single developer laptop to a global enterprise architecture. As an architect, your job is to weigh the near-instantaneous performance and simplicity of local streams against the boundless scalability and centralized governance of networked HTTP transports. You must intimately understand the life cycle of that SSE connection, the routing mechanics of the decoupled post requests, and the critical importance of last event ID for state reconciliation. You must treat every network boundary as a hostile environment, enforcing encryption and mutual authentication at every step. This mastery of the transport layers is what separates a novice developer playing with local AI tools from a senior engineer capable of designing production-ready, fault-tolerant agentic systems. We have now thoroughly charted the entire foundational landscape of the protocol. We have examined the precise JSON RPC message structures. We have dissected the life cycle of initialization and capability negotiation, and we have exhaustively compared the local and remote transport mechanisms. You now possess a rock-solid understanding of exactly how bytes flow between an AI model and its tools. But transport is only half the equation. Now that we know how to move data, we must understand the data itself. In the upcoming modules of this comprehensive series, we will finally pivot away from the transport layer and dive deep into the semantic core of the Model Context Protocol. We will explore the structural schemas that define tools, resources, and prompts, and we will analyze how the model dynamically discovers and reasons about the capabilities exposed over these streams. We will get into the weeds of JSON schema validation, pagination, and the precise mechanics of tool execution.
The journey is just getting started, and the upcoming modules will truly unlock the cognitive potential of the protocol. We highly encourage you to review the concepts from this audio session, perhaps listening again during your next deep focus block, to ensure these transport architectures become second nature. Understanding the foundation is the only way to build reliable superstructures. Keep pushing your technical boundaries, stay curious, and remember that mastering these granular details is the key to advancing your career in the rapidly evolving landscape of localized AI.
Well said, Maya. This concludes Module 2 of our deep dive into the core architecture and transports. Make sure to subscribe, save the full playlist, and prepare for the next intensive session. We are committed to providing the highest density of technical knowledge available anywhere. Thank you for dedicating your time to mastering the craft. And as always, keep building the future with Vinkius Labs.